Hello everyone, I'm Chungsu Kim and I will present our team's final project titled Combat Situation Recognition Model using Sound Data. This is context for presentation. This presentation will cover project purpose, response to feedbacks, dataset feature extracting, machine learning models, model result, value of research, and follow-up studies. In contemporary warfare, robots, particularly drones, play a key role. However, challenges arise in urban settings with numerous obstacles or during wartime situations where using visual data becomes difficult. Our project aims to create a model detecting the presence of people or military transportations using sound data rather than visual information. In this slide, I will discuss our response to feedback. Firstly, differences from previous studies. Our project is applied in war situations, setting it apart from prior research. Secondly, we addressed the challenge of utilizing auditory data when visual data was impractical in certain situations. Thirdly, feedback was provided regarding data balance. By combining datasets, we generated 10,000 pieces of auditory data that could be heard in real-world situations. The sound data was sourced from the open dataset. We randomly selected background sounds in a war scenario, mixing elements like weather, guns, and bird sounds. Next, we introduced human sounds such as running and walking into the previously created background sounds. Also, we introduced military transportation sounds such as panzers, tanks, armored cars into the background sounds. Each of class contains 10,000 of sounds and sound duration is 10 seconds. As an example, I will provide an audio demonstration. I will talk about feature extracting in this slide. MFCC was used to select features. This is very useful in machine learning and deep learning as a method of selecting sound features in consideration of human sound perception characteristics. It was selected because the amount of computation was less and generally showed better performance compared to a similar method, mass spectrum. The number of coefficients was set to 13, which is generally used, and it was also tried with 8 for parameter tuning. In the figure, the bottom left is when the number of coefficients is 8 and the rest is 13. Comparing the two below, it can be seen that the resolution is slightly different. We used RNN and LSTM as deep learning models. RNN is a model that receives a given audio characteristic as input, learns the pattern of the time series data, and classifies it into one of the categories. However, RNN has a problem in that long-term dependence is not handled well, and learning in long sequences is difficult due to the gradient loss problem. LSTM is a model that improves the problem of RNN and is designed to solve the problem of long-term dependence. In addition, we employed two machine learning models, CNN and KNN. CNN is a model that incorporates the concept of residual learning, allowing effective learning of less than 50. KNN, on the other hand, is a simple and intuitive machine learning algorithm. It predicts by majority voting among its k nearest neighbors in supervised learning. The optimal value of k varies from each MFCC. When MFCC is 8, best k value was 9. When MFCC was 13, best k value was 13. The table below presents the results for each model. We performed model training by splitting the MFCC numbers into 8 and 13. When set to 8, as indicated in the table, CNN attained the highest accuracy at around 70% with the fastest processing time of 4.448 seconds. On the other hand, when MFCC was set to 13, LSTM achieved the highest accuracy at about 92%, while CNN demonstrated the shortest processing time at approximately 11 seconds. Next, I will talk about the value of our project. We successfully built a model that distinguishes target sound data in a mixture of noises. Model trained through LSTM demonstrated an accuracy of approximately 92%. Surprisingly, traditional machine learning approaches also showed significant results. KNN achieved a similar level of accuracy with RNN, about 86%. This implies that models with relatively lower memory requirements can effectively address the problem. Through these results, it is inferred that the models we trained could be used to detect the movements and positions of hidden enemies in combat situations. Challenges in accurately classifying or distinguishing data may be compensated by using additional combat data or installing a number of fixed sensors. Finally, I would like to conclude by discussing follow-up studies. Firstly, although we employed a relatively deep model for CNN, LSTM and RNN used a shallower model. Therefore, constructing deeper models for LSTM and RNN could potentially enhance accuracy. Secondly, we observed significant variations in the model performance based on the number of MFCCs. Conducting research to identify the optimal value for MFCC to improve accuracy could be valuable. Thirdly, increasing the volume of data could lead to accuracy improvement. Lastly, our ultimate goal is to conduct research not only with mixed data, but also by acquiring sound data from actual battlefield scenarios, aiming to generate practical models. With that, I conclude the presentation. Thank you for your attention.